Okay, let's talk about one of the most incredible manufacturing feats happening inside you, like right now. We're about to go on this amazing journey, starting with a single stem cell and following it all the way until it becomes a specialized oxygen carrier. This is the story of erythropoiesis. You know, how our bodies actually create red blood cells. And you're not going to believe this. Every single second, your body's churning out about 2 million of them. It's wild. So let's see exactly how that miracle happens. All right, so here's our game plan. We'll kick things off with the what, why, and where of it all. Then we're going to trace the path from stem cell to erythrocyte. After that, we'll get into building hemoglobin and managing iron. Then we'll look at the control systems and nutrition. And finally, we'll explore how it's evaluated and what happens when the system fails. All right, first up, the what, why, and where. We're going to uncover the fundamental purpose and, the location of where all these red blood cells are actually produced. So what's the big mission here? It's all about oxygen homeostasis. I mean, it's making sure every single tissue in your body gets the oxygen it needs to survive. That's the red blood cell's one and only job. And the rate is just staggering. We're talking 2.4 million new cells every second to make sure we don't have tissue hypoxia. Now, if you look at this life cycle diagram, you can see the whole story. It starts in the bone marrow, right? That's a 7-day process to build just one cell. Once it's out in the world, it circulates for about 120 days. Then it's time for retirement. It gets taken out, usually in the spleen. But, and this is the really cool part, nothing goes to waste. The iron from that old cell, it gets recycled right back to the bone marrow to build the next generation. It's a perfect loop. What's interesting is that this cellular factory, it doesn't just stay in one place. It actually moves around as we develop. When we're just tiny embryos, production starts in the yolk sac. Then, the liver and spleen take over for a while. By the time we're born and all through our adult lives, the main production hub is our axial bone marrow. Think spine, ribs, pelvis. But here's a really fascinating clinical correlation. If something goes wrong with the bone marrow, say from a severe anemia or a disease, the body can actually flip a switch and reactivate those old fetal sites, so the liver and spleen can start making red blood cells again. This is called extramedullary hematopoiesis, and it's why you sometimes see those organs get enlarged in certain conditions. Okay, so we know where the factory is. Now let's head inside and look at the assembly line. This section is all about that journey, from stem cell to erythrocyte. We're going to see the detailed maturation process. So everything kicks off with this one master cell, the hematopoietic stem cell, or HSC. And this thing is incredible. It can either make a perfect copy of itself, to keep the pool of stem cells going, or it can start to differentiate into any kind of blood cell. For our story, it first becomes a common myeloid progenitor, the CMP. Then it specializes even more, becoming a megakaryocyte erythroid progenitor, or MEP. Now, this next step is the crucial one. It's the point of no return. A couple of transcription factors, GATA1 and KLF1, get activated, and that's it. That's the irreversible decision. The cell is now fully committed to becoming a red blood cell. The switch turns on all the right genes for making hemoglobin, and we get our very first recognizable precursor, the proerythroblast. Okay, now this is really cool because you can actually see the maturation happening. Just look at the trends as we move from left to right on the screen. See how the cells get smaller and smaller, and the color inside, it shifts from this deep blue all the way to a pinkish red. And the nucleus? It just keeps shrinking until it's gone. So it all starts with the proerythroblast. It's big, and that deep blue color tells you it's jam-packed with RNA, building all the internal machinery. Next up is the basophilic erythroblast. It starts making hemoglobin, but it's still mostly blue. The big shift happens at the polychromatophilic stage. Poly means many, chroma means color, and you can see why. It's this awesome mix of blue RNA and pink hemoglobin. And finally, you get the orthochromatic erythroblast. It's almost all pink now, just loaded with hemoglobin. Its work is done, so the nucleus gets kicked out. And those bars at the bottom perfectly show the story. RNA goes down, hemoglobin goes up. So once that nucleus is gone, we're left with the reticulocyte. This is the stage that leaves the bone marrow and enters the bloodstream. Now, it doesn't have a nucleus, but it still has some leftover RNA that looks kind of like a net or a reticulum under the microscope. That's where it gets its name. It hangs out in the blood for about 1 to 2 days, and this is super important because it's a key clinical marker for how well the bone marrow is working. After those couple of days, it ditches the last bits of RNA, and voila, it becomes the mature erythrocyte. And this final form is just a masterpiece of biological engineering. It's this flexible, biconcave disc with no DNA, no mitochondria. It's perfectly, and I mean perfectly, optimized for one thing: gas exchange during its 120-day life. Okay, let's zoom in even further, down to the molecular level. Next up, building hemoglobin and managing iron. We're talking about the critical payload and its core component. At its heart, the equation is pretty simple. Heme plus globin equals hemoglobin. But making it happen is this really elegant, coordinated effort. So first you have heme production. This gets started inside the mitochondria, and it's driven by an enzyme called ALA synthase. Now this is the rate-limiting step, the bottleneck for the whole process, and it needs vitamin B6 to even work. So that's one part. At the exact same time, over in the cell's ribosomes, the globin protein chains are being built. Then comes the final assembly. You take 4 of those heme groups, each one grabbing an iron atom, and combine them with 4 globin chains. Put them all together, and you have one complete, functional hemoglobin molecule ready to carry oxygen. And this image, it just perfectly lays out the entire supply chain for iron. So let's follow it. The journey starts in the intestine, where we absorb it from food. But then it hits this crucial checkpoint, which is controlled by a liver hormone called hepcidin. Seriously, think of hepcidin as the bouncer at the club door. If hepcidin levels are high, and this happens a lot during inflammation, the door is shut. Very little iron gets into the blood. But if hepcidin levels are low, the door swings wide open. Once it's in, iron needs a taxi. It hops onto a transport protein called transferrin. And transferrin takes it to one of 2 places, either straight to the bone marrow to be used right away, or off to the liver and other spots for storage as ferritin. All right, so we've built the cell, we've built its payload. Now, what about the bigger picture? Let's talk about the control systems and nutrition, the regulatory networks, and all the essential ingredients you need. So how does the body know when to make more red blood cells? Well, it's this classic, beautiful, negative feedback loop. Let's just trace it around the diagram. It all starts with a trigger, tissue hypoxia, meaning low oxygen levels. The kidneys are the sensors here. They detect the low oxygen and they go, hey, we need more oxygen carriers. So they release the hormone erythropoietin, or EPO. EPO then travels to its target, the bone marrow, and basically tells it to ramp up production. It stimulates the red cell precursors, telling them to grow and multiply, and the response? You get more red blood cells, which means better oxygen delivery. And once oxygen levels get back to normal, that tells the kidney, okay, you can stop now. The kidney stops releasing EPO, the signal is cut, and the whole system stays in perfect balance. It's brilliant. You know, this whole production process doesn't just happen randomly. It's super organized. Inside the bone marrow, the red cells develop in these specialized little clusters called erythroblastic islands. And right in the middle of each island, you've got this big macrophage that acts like a nurse cell. It's amazing. It does 2 critical jobs. First, it literally hands off iron directly to the baby erythroblasts. And second, it plays cleanup crew, gobbling up the old nuclei that get kicked out during maturation. It's this incredibly efficient and supportive little neighborhood for making red blood cells. Okay, so this entire assembly line is completely dependent on having the right raw materials. Let's go through the shopping list here. First, and most obviously, iron. It is the absolute core of the heme molecule. If you don't have enough, you get microcytic anemia. The cells come out too small. Next up, vitamin B12 and folate. These guys are crucial for making DNA. Without them, the cells can't divide properly, and you end up with megaloblastic anemia, where the cells are weirdly large. Then you've got vitamin B6. Remember that enzyme that kicks off heme production? Well, B6 is its essential co-pilot. A shortage leads to something called sideroblastic anemia. And finally, of course, you need amino acids. These are just the basic building blocks for the globin protein. Not enough of them, and the whole production line just slows way down. Okay, time to shift gears and look at this from a clinical perspective. Let's talk about evaluation and system failures. How do we actually diagnose problems, and what happens when this amazing production system fails? So one of the very first things a doctor will do is look at the cells on what's called a peripheral smear. This lets us check out the mean corpuscular volume, or MCV, which is just a fancy way of saying the average size of the red blood cells. So if you look at the image on the left, you see microcytic cells. They're too small, with an MCV less than 80. That's your classic sign of iron deficiency. Now the picture in the middle shows normocytic cells. They're the just right Goldilocks cells, with a normal MCV between 80 and 100. And over on the right, you've got macrocytic cells. These guys are too big, with an MCV over 100, and that immediately makes you think about a B12 or folate deficiency. Now, here's a really important clinical pearl. If a patient is anemic, a normal reticulocyte count is actually really bad news. It means the bone marrow isn't responding. So we have to correct for the anemia using something called the reticulocyteproductionindex, or RPI. And the logic is simple, as you can see in the flowchart. If you calculate the RPI and it's greater than 2, that's good. It means the marrow is responding properly, it's churning out new cells to compensate for something like hemolysis or blood loss. But if the RPI is less than 2, that points to a problem with the factory itself, a production defect, or marrow failure. It's a surprisingly powerful little calculation that helps pinpoint the source of the anemia. So when production does fail, the problems usually fall into one of 3 main categories. First, you can have production defects. Think of this as a supply chain problem. You're short on resources. This includes things like iron deficiency anemia or the anemia of chronic disease. Then there are maturation defects. Here, the factory has all the supplies, but the blueprint is flawed. It's making the cells all wrong. That's what you see in disorders like thalassemia or myelodysplastic syndromes. And finally, you have the most serious category, marrow failure. This is when the factory itself is just shut down. The lights are off. This is where you'd classify something like aplastic anemia. Which brings us to this expert-level definition that just wraps everything up so perfectly. Let's read it. Erythropoiesis is a hypoxia-driven, transcriptionally regulated, iron-dependent differentiation cascade. Whew, that's a mouthful, but every single part of that sentence captures something we've just discussed, right? It's driven by low oxygen, regulated by genes, and totally dependent on iron. In the end, it all comes down to maintaining this delicate balance between the supply coming from the marrow, the demand from our tissues, and the resources we have on hand. And really understanding that equilibrium is the key to interpreting all those vital clues hidden in a simple blood count.